Thank you all. Thank you for having me back. That is the third GeeCON I've been at in the third different city. I was in Sopot many years ago for a special microservices edition. I was in Prague, and now I finally get to come to Krakow for this one. I've talked about different topics over the years, and today also as a keynote, and I guess that is why it is a keynote, I want to talk about one topic that should really concern all of us. And that is the topic, of course, of sustainability. We have a lot of issues with our planet, with global warming and so on. And that is something I think that we in the profession of writing software, of building systems that run everyday's business, also being at the forefront of the AI changes that we are now seeing, that we should now, in this day and age, should take into account right from the beginning. I work at Thoughtworks, which is a global consulting company, so I do get a lot of insights into what large and small organizations around the globe are doing, but I'm also engaged, and Thoughtworks is a founding member of the Green Software Foundation. And if you are interested in this topic, I would really recommend that you check out their website or our website. There's a number of different organizations, of course, involved in the Green Software Foundation, but I do think this is something where a number of different companies from different fields have come together to think, but also act on what we can do. There is, of course, when we're in IT, a number of different areas where we could talk about sustainability. And as we geeks do, we often like binary things. So we have often seen people talking about either sustainability by IT or sustainability of IT. And I guess just by the naming, it's relatively obvious what we're talking about here. The by IT means we're using IT solutions to make something else more sustainable. And that is definitely worthwhile considering, and I think there's a lot of things we can do, a lot of software optimizations we can build to help that side. What I want to talk about today, though, is really sustainability of IT. This is the area of actually making the software that we write and deploy and run more sustainable in the way this is done. I don't know about you. When I talk about this topic in many large organizations, people often wave away sustainability of IT. They're saying this is only really a small part of what we do. It is it's a one-digit % figure of the carbon emissions that we are responsible for. So why would I even bother? Why don't I look at all the other things? What I would argue, though, is that if we always do that, if we always look at the one that is bigger, we can keep pointing and pointing and pointing until we find just one and all the hope rests on one party. While I think if we all in the smaller areas are doing our part, that will also add up. It's impossible, and you will see this throughout the presentation. I've really tried to give you the sources of the material. It's not easy to come by, but and sometimes the material is also really contradictory. But in the end, I guess, the current best estimate is that the data centers in IT are using roughly 1.5% of the global electricity. So while you could argue there is bigger polluters out there, there's other areas that is already a sizable number. And if we can shrink that, I think we could do something really well for the environment, for sustainability as a whole. And that is also mirrored by some of the more forward-thinking organizations that we're working with. So this is what today's talk is really going to be about, sustainability of IT, what we as engineers, as software engineers, as infrastructure engineers, and so on can do to help in that area. The talk is in 3 parts. The first 2 are really talking a little bit about the concepts behind that I feel are absolutely necessary to understand. Some of the concepts may be familiar with you. I hope you'll still get something out of it. And then in the third part, I'm going to give you some examples of what we can do concretely, although I hope you will take away some other ideas what you could do from the first 2 parts as well. The first one is about carbon efficiency. And here, what we often talk about is this letter soup, really, CO2e. The E doesn't actually stand for emissions. It's carbon dioxide equivalent. So there's many different greenhouse gases. Some of them are much more dangerous for the atmosphere. Methane, for example, is about 40 times as much heating the atmosphere as CO2 would do. But I mean, we need to standardize and both the technologists as well as the business people try to have a minimum number, a small number of metrics that we can optimize. So there's a couple of formula, a couple of simplifications, honestly, also, that are being made to come up with one number, and that is the carbon dioxide equivalent, the amount of greenhouse gases that are caused as emissions through whatever we are doing. What I will do as another simplification in this section is I will say there is a strong correlation between the carbon efficiency, or the CO2 emissions, and the energy efficiency, the amount of electricity I'm using. I'll explain a little bit what I mean by that, and I will then later talk about why that is not always the case and what we can think about that as well. The first important concept is, it's always easy, right? What are the others doing? I mean, if we are software engineers, if we're infrastructure engineers, if we use on-prem data centers that we lease somewhere, or the public cloud, somebody needs to run the data center. So let's first look at the other folks, the ones that we can't influence that much. And the concept here really is PUE, power usage efficiency. And what that means is, for all the servers you're running in the data center, there's other electricity use. And you can see the example here. This is probably a medium to large size data center. It consumes 10 megawatts of electricity, and everything else around it, the light, the air conditioning, the UPS systems, they consume another 2 megawatts on top. This is just to run the servers. That means, of course, the data center is pulling 12 megawatts from the electricity grid, and the factor, the PUE factor, I think with these numbers it's easy to see, is 1.2. So 1.2 is a factor of what we're actually using with the servers is the overall consumption. And of course, the PUE factor can never go below 1, because then you would have nothing but the servers. It could go arbitrarily high. I remember 20 years ago, people thought or said that in certain data centers you could add the same amount that you were using for a server on top for air conditioning. We've gotten much better. I'll go into more detail about this number later. 1.2 is a pretty decent factor here. The other thing we can't directly do anything about is how are the servers made? Because there is not only the electricity that is being used, but there's also, of course, the carbon emission that are caused by the production of the server. And what we can see here is, again, the data is really incredibly hard to get by. This is from a study that was commissioned by Dell. It's incredibly detailed. If you want to read it, the link is somewhere in there, and I guess you will get the slides later. So it's a 70-page study with a huge amount of detail for a pretty standard Dell server. If you now think, I don't have a Dell, whatever this is, an R740, I have another variant, I'll get the report for that one, won't happen, at least not easily. The server makers are not publishing these kinds of reports for all the different servers. It's really only certain ones where they make the effort, and we have to extrapolate from those. But it is insightful anyway. With all the assumptions they made on this one, you can see this here on the column chart, about half the CO2 emissions are caused by the production of the server itself. And only the other half is really caused by the electricity that is being consumed while the server is running. You can also see the transport to the customer and the transport to EOL, end of life. It's really negligible, I would say. And if you wonder why there's a negative number at the end for end of life, the assumption here is, of course, that you recycle some of the materials that were used in the server and you're getting those back. I'm not sure whether that's immediately obvious from looking at that chart, but one of the key assumptions, of course, is how long are you using that server? Are you using it for 2 years, for 3 years, for 5 years? And I think you can immediately understand, not see in the diagram, but understand that if you were to double the lifetime of the server, the bar chart or the column with the use would go up significantly, because you would use it for a longer time, you would consume more electricity. The production cost is not going to change. The amount of carbon that was used to produce the server remains the same. So by using hardware longer, you can tilt this in our favor. It depends how much influence we have over the data centers that are operating the servers, but it is definitely something to bear in mind. This is also, by the way, one of the reasons why, from an environmental perspective, it's really good to use your mobile phone for more than 2 or 3 years. For mobile phones, and there are similar charts for mobile phones, almost all the CO2 emissions are for the production, because they use so little electricity. They are so optimized not to use much electricity. So if you're throwing out a phone after 3 years or 6 years, you're almost halving the CO2 emissions on an annualized basis. I hope that makes sense. It's going to get a little more complicated because the servers are also not, they're proportional, and I'll show you real figures later, but if you look at the load that is on the server, how much am I using the server and how much electricity does it use, there's proportionality. Of course, a server that is doing more computations will use more electricity, but a server that is sitting idle doesn't use no electricity. It still uses electricity. The numbers have gotten much better over the years. This is from a study done by Microsoft a few years ago, but you can see the line is crossing the y-axis at about 25%, I would say. So a server that is not used, that you've just leased, that you've just bought in case, because you need to scale, you have to prepare for some peak load, the server is running, you're still using 25% of the electricity. What is really interesting, and this may look like a little math trick, and in a way it is, but especially in the lower part of the diagram, you can see an interesting dynamic. This is just the figures, right? I can increase from 10% load to 40% load, so the server is doing 4 times as much work, but I'm only increasing the electricity by 70%. So what I'm saying here is a server that is hardly used is a lot of potential there to actually increase or decrease the carbon emission, increase the efficiency. What we can also look at, though, is the programming language. And I'm at a Java conference here. I promise I didn't change the slide for a Java conference. I'm using that slide when I'm giving the talk in other places as well. And Java does come out reasonably well. Again, there is not a huge amount of research in that space. And again, there's a lot of assumptions that need to be made. But this is a well-regarded, I would say, paper done by a team of researchers. This is actually a few years old now. And they looked at the energy efficiency of programming languages. They took a number of standard benchmarks. Unfortunately, they were the typical, more compute-oriented benchmarks. I would have loved if they had used a benchmark that shows like a web application server running, only doing light computation, maybe a bit of templating, serving JSON, or making database queries. That is not what we're seeing here, but it is still a pretty decent approximation. What the authors have done, I mean, there's more in the paper. I'm showing you just one diagram that I feel, for the purposes of today, is the most relevant. What they have done is they've used the C programming language as the benchmark. So C gets 1, a factor of 1, and then all the other languages are shown in relation to that. And you can see that a language like Rust and C++, which are compiled to bare machine code, are getting very close. In fact, I was a bit surprised about C++. I think it has to do with the way of how the method dispatch works on virtual methods here, that it didn't get closer to C and Rust, but we see that they are relatively close. What I was impressed about is that Java, as a not natively compiled language, but something that runs in a virtual machine, is doing that well. I mean, I already knew the JVM has seen so many optimizations. I have a great amount of respect for the engineers who are working on the JVM, but it was still surprising for me to see that it is only, in scare quotes, only a factor of 2, that is less efficient. What is interesting is that you can see this, and that's why I left the other column in there. I'm showing the energy efficiency and the time efficiency. So how long does it take to complete the program? And what we can see is, and you can see this easily in the chart, for most programming languages, the 2 columns are very similar in size, which means we can make another simplification. Rather than talking about how much energy something is using, we can talk about how long does it take to run. That also feels intuitive for us as engineers, right? I mean, if a program takes longer to run, we assume it takes more energy. An interesting outlier in this case, by the way, I don't know whether you spotted it immediately, is here, is Swift, which is actually the blue one is the time. So it's actually a bit slower than the others, but it's still very energy efficient. And I guess you can make an educated guess why that is. This is designed by Apple to run on mobile phones. And one of the key things they want is, of course, the programming language to be energy efficient, so you get a long battery life out of those. What is interesting, though, is also, of course, the JavaScript line here. JavaScript is hugely optimized. I'm often impressed by how much they got out of it. But still, what we can see here, it's a factor of 2 worse, actually, than Java. So the naive, but still somewhat correct assumption is if you're implementing the same algorithm, if you're implementing the same server in JavaScript, you're probably using twice as many resources as if you implemented that in Java. You need to put that, of course, into relation of the capabilities of your organization and other constraints. I would certainly not advocate, because you could make the same argument saying, why would you stop at Java? Why don't we write all the microservices and web servers in C? I certainly wouldn't advise to go there, but it is an important factor to bear in mind. One thing that maybe you find, I don't know, shocking or surprising is Python. And I don't know, this is a log chart. You can see this on the y-axis, right? I mean, this is a logarithmic scale. So Python is really 70 or 72 times as bad as C in this comparison. And then a lot of people are saying, oh my, Python is used for machine learning. This is terrible. This is a terrible waste. But here we shouldn't forget that most of what Python is doing in machine learning is really a glue language. It is only used to glue together some library functions to call other things, and the actual core of most of those is implemented in relatively efficient C or even in specific like GPUs, TPUs, NPUs, specific hardware, so that if you're building a machine learning system, it is not as bad as it may look here. Okay. Second major topic. We talked about carbon efficiency. Let's briefly talk about carbon awareness. So here, this first unit is grams of CO2 equivalent per kilowatt hour. So it's basically saying how much carbon emissions am I responsible for per unit of electricity being used. Of course, the geeks among you might say, what is the kilowatt doing there? You could just say watt hours. It's a scaling factor. The industry has settled on using it by dividing by an extra 1,000. Energy is not always the same. I've taken here a screenshot of a site that gives data about the electricity mix in the standard grid. And this is a picture from Germany for a week at some point last year, and you can see the 7 days. You can see the yellow part, that is helpfully solar energy. The green part just below it, this bit here, is wind energy. And the black line shows you the actual use of electricity throughout the day. During the day, of course, there's more electricity needed. Then people go home, make dinner, watch TV, stream on their preferred streaming service, and then they go to sleep and less energy is used, and then the whole thing repeats. But what you can see also is, of course, that solar energy is only available through the day. The wind energy is somewhat constant in that week, but we can also see here when the sun goes down, the other energy sources are really ramping up. So you see a lot of fossil fuels here, gas, coal, oil even. People are talking about the idea that during the day when you have excessive energy, you can pump up water, for example, and then you release it down the hill again to generate electricity. That is actually being done. I'm not sure you can see it here, the little blue bit here. So in that peak after the sun goes down, that is being used, but it is not really helping. So what does it mean for you? So if you run a workload at that point in time, the electricity mix in the grid is relatively bad. So if you were able to shift it to, say, to that part of the day, without changing anything, without making your software more efficient, you would still become greener, because the electricity you're consuming on the whole is more green, comes from more renewable resources. And you can also see at the top here, there's a bit of excess energy being produced that, or could be produced, that is not really needed, as the black line shows. It would almost be for free even. You can see at the bottom when it goes below, these are exports across the border. But you can also do this maybe overnight. You can see here, the sun is not shining, but the overall use of electricity has gone down so much that, again, there's a bit of overproduction, in this case of wind power, so that anything you do to get away from that point A to points B or C would immediately reduce the carbon impact you have. At the same time, of course, this also needs to work for the solution you're building. I mean, if you have say a B2C e-commerce website and you have a lot of people putting items in their shopping cart and researching products on your website, you can't really tell them, we need to shift our load to another time of the day. Please visit our website when there's more wind power or when the sun is shining. You can't do that, right? But there are certain things that you can shift. And then similarly, not only in time, there are certain workloads you can also shift geographically. This is another website called Electricity Maps, which actually gives you accurate data. I took this screenshot yesterday afternoon, an updated version, and here you can see, sometimes by country, sometimes by region, how carbon efficient the electricity generation is in that country, or how green it is. One thing I would say is, I picked Finland here because you see Finland is 98% green electricity, but only 68% renewables. So that's an important thing to remember. If you look at those sites, nuclear power is considered green. And they, of course, don't take into consideration all the CO2 emissions from building a nuclear power station. But I mean, green energy means no carbon. So for the purpose of what we're doing, it's correct. It just might not overlap 100% with what you would consider green. And it doesn't, in all the countries, mean automatically renewables. And you can see this in France, which is a big country for nuclear power. And that's very green here because they create a lot of carbon-free emissions. What is also interesting is you need to look at the consumption and not the production, especially here in Europe. There's a lot of cross-border exchange. So you don't want to know what the country that you are operating in produces, but you want to see what it consumes. The large IT companies or the large consumer electronics companies are beginning to exploit this, not necessarily everywhere in the world. I don't even think in Europe at the moment, but for example, Microsoft with the Xboxes, they are trying to do the updates of the Xbox software when they know the electricity mix is good in the grid. And similarly, Apple tries, at least in some of the states in the US, in California, for example, where they have the data to optimize the charging of the iPhones overnight to a time when the mix of electricity in the grid or when there is more renewable energy available. That is not something I guess most of us can do. I don't know exactly where you are working, but for us it is actually often more easy to just think about the enterprise workloads, the cloud computing centers. These are things you can actually shift. I mean, we do have customers who train their own large language models. We're seeing definitely a trend away from that. It's very hard. I mean, it's expensive to start with, but it's also difficult to get right. So most of the time we suggest that organizations are using foundational models that are trained by somebody else and then use something like, say, retrieval augmented generation or other techniques to use those foundational models. But in certain cases, they are still either because they're specialized areas, the need to train a large language model, but there's also all sorts of other things in machine learning. Just because we have language models these days, we still have all the other machine learning that we had in the past available to us and being used as well. And these jobs, they can often be moved. It doesn't really matter. Do I need to train the model at 7 p.m.? Do I train the model at 3 a.m. in the morning? Or do I train it when there's a lot of sun? Or do I train the model in a country like, say, Sweden, where there is a lot of renewable energy, or do I train it in, say, like a country like Ireland, where there's not so much renewable energy? So here we can move. Interesting, this is, I don't know whether you're familiar with Hugging Faces. It's a website that allows you to download and also upload, if you're a researcher, I guess, language models. And this is the model card for Stable Diffusion, which is the open source image generation one that I guess many of you have probably seen. And they provide some information here. They're saying they use these A100 GPUs from NVIDIA for 150,000 hours in AWS US East. And they said that cost about 11 tons of CO2 emissions, which is a sizable number, I would argue. So if you could reduce that, at the same time, you have to be, even when you're not constrained, say, by latency or by availability in time, sometimes the hardware simply isn't there. Maybe the people at whoever did, I can't remember right now, whoever did Stable Diffusion, maybe they were aware of it and they said, let's train this in Sweden. And then AWS said, but we don't have the hardware in Sweden. You have to go to US East. This is where we have physically installed these graphics cards. But as I said, it's definitely an avenue worth pursuing. So, as a summary of this, how do we think about green software? On the one hand, we can think about carbon efficiency to make the software more efficient, to use less hardware or use the hardware in a better way. Or on the other hand, be carbon aware and shift the load where we can in time or space to an area where we are causing less CO2 emissions. As a baseline, though, we need to understand how much emissions we're actually causing. And as I said, in the first section, I really talked about almost as if it was a direct relationship, and I explained later that the electricity mix is a bit different, but how do I know about my solution? And people often talk about measuring. I definitely did want to change that perception and added the word estimating here, because a lot of the measurement is also estimation in reality. Etsy, I don't know whether you know this website. It's a website for handcrafted goods. It's quite popular throughout the world. It's a client of Thoughtworks. We worked quite a lot with them. And at some point, they wanted to move away from the software that was running in their own data center to the public cloud. They chose GCP at the time. And they also had a mission, and I guess if you know their handcrafted items, you can assume that they were early on quite interested in their carbon footprint and wanting to reduce it. They were educated enough about it, of course, that they had a strategy and that they also thought that sheer reduction is not necessarily the goal. It needs to be related to the development of the business. And that's a chart. All the pictures, that the previous one, this one, and the next one, are from Etsy's website, from a blog post that they did. So what you can see here in the middle, you can see the business is developing and the energy consumption goes up with the business. That's considered acceptable, right? If you have twice as many customers, it's actually not a regression. It's not terrible if you use twice as much electricity. What you definitely don't want is the other relationship, that even if your business grows, the electricity consumption grows even more. That's what you absolutely want to avoid. But where you want to go really is that as your business grows and you get more users, it's proportional, but with a lower slope, so that you do use a bit more electricity, but not directly related to it. And that's where they want to go. How do you know? In their own data center, they could actually just measure how much electricity they were using, because it was their own data center, right? I mean, they got the electricity bill at the end of the month. When they then started to move to GCP, of course, they could not get the electricity data from Google. They're not making it available, but how would they anyway? Because there is so much in the data center. You're sharing the data center with many other companies, so they couldn't. So what Etsy did at the time is they came up with a way to estimate, and I'll explain that in a minute, what their CO2 emissions or the energy usage, actually, they didn't even talk about CO2 emissions, what their energy usage would be. And what you can see here is you can see this, the old data center, and as that is ramping down, as the workloads are shifted to GCP, the usage of GCP goes up. One thing I want to highlight here is actually the PUE. In their own data center, they had a PUE of roughly 1.4. In the Google data centers, and unfortunately the cloud providers don't give you specific numbers for each of the data centers, you only get the average numbers across the world, but Google is saying that their PUE is only 1.1. So just by moving the same workload, you're reducing it from, say, 140 to 110, which is a 20% reduction right there. So that is interesting. I mean, the cloud providers have such an incentive to reduce to decrease the PUE factor because it saves them money, and they have the scale and, frankly, also the right people to do this in a way that is really, really difficult to match by other organizations. So, luckily for everyone, Etsy made all the things they had designed available as open source software. They called it Cloud Jewels. Thoughtworks is a company that also loves open source software, so we took the Cloud Jewels ideas, some of the code, and created an open source tool called Cloud Carbon Footprint that allows you to estimate the carbon footprint across multiple different clouds. That, and the arrow here is going to show, Cloud Carbon Footprint is now being used as a basis for other things. The Green Software Foundation has introduced the impact framework. Google has built some tools on top of that. So that is really something that has had this kind of history from real practical innovation. How does it work? Most of them work in the same way, to be honest. First, you try to get usage information. And there's normally in the cloud providers, there's an API for that. In AWS, Cloud Carbon Footprint uses the cost API. In GCP, the billing API. In Azure, there's a consumption API. So you get in the left stack here, you get all the, you can see that, right? Yeah. In the left stack, you can actually see the different areas we're looking at. The Etsy software only used compute and storage, and that's by far the most important one. Networking and memory. Memory as in the RAM is actually not as relevant, but because we could, we added it. Now you only know how much compute resources you have used. How much electricity are you using? And that's where the energy conversion factors come in. And most of the time what we do is we use a database called the spec power database that has entries for almost 1,000 server systems that give you precise information. Here's an example of it. This is actually the same Dell server I showed you before. And you can see here is a big table that shows you a 10% load, a 10% target load. It achieved 10% load and it used 114 watts of electricity. At 100% load up here, it actually used 432 watts of electricity, and you see more information up here. This chart here is, you have to flip it mentally, and I'll do it for you. If you change it, you can see the chart that I showed you earlier with the energy proportionality. So you can see now the load increasing, and in blue you can see the power usage increasing. So you're seeing this server is actually quite good. At zero load, at idle, it only uses 10% of the maximum power, but it does go up, not linearly, but also slightly superlinear. There's also something to be said about the efficiency of the server itself, but that's for a more detailed look at that. So, after we've multiplied, and this is like kind of pseudo math, so we take the usage, we multiply it by the conversion factor, which gives us the amount of electricity we need. Then we multiply by the PUE factor that you've heard about before. And in the end, we need to look at the grid emission factors. And here, in the end, as so many other areas, when we don't have data, Cloud Carbon Footprint uses some published averages, but where the data is available, the tool uses actually more detailed information. Again, it's not an easy world at the moment. Here's a report that was done by Google, which is actually quite helpful. But this is not a dashboard you can look at. This is a PDF file, a study that they did and uploaded and made available. But here you can see, for example, for the Europe regions, how much carbon, CFE is the abbreviation for carbon-free energy here, how much carbon-free energy the different regions are actually using, and they helpfully point out the ones that are low CO2. So maybe it is worthwhile to shift something from, say, from London to Finland, because you are saving or you're reducing the footprint a little bit. But as I said, the data is changing over time. And then with that, you actually do have carbon emissions for the electricity. What you then want to add is you want to add the so-called embodied carbon, that is the carbon that comes from the actual production of the servers. That needs to be added on top, of course. This is not the electricity you used, and as I showed you on the earlier slide, that can be quite significant. And in the end, Cloud Carbon Footprint, but other tools as well, they can provide a chart like this, and you can see that over time, you can actually see this correlation between the CO2 emissions and the kilowatt hours of electricity being used. And you can see that most of the time they're closely correlated, but here, for example, on those dates, you see a difference. This is data we recorded and anonymized. I don't know where it came from anymore, but I mean, you can see that it is not always the same. But in the end, what is really important is that you have something that you can compare. And that was also, if you, for example, take what Cloud Carbon Footprint estimates, and you compare it with, for example, the solution that Google has built in their cloud, and I've copied the video in here because it's actually quite a fancy tool. It's way fancier than what we've built with Cloud Carbon Footprint at that stage. But at the same time, the tools that the cloud providers give you, they only work in their respective clouds. So the Google tool works in GCP, the Microsoft tool works in Azure, the AWS tool works obviously in AWS, and some of them are a bit flawed. The Microsoft tool, for example, you have to pay to use because it needs Power BI. The AWS tool doesn't give you CO2 emissions that include what is their Scope 3 emissions, the production of the hardware. So in the end, you have to compare this a little bit. And in the end, the numbers will not match up entirely. But at the same time, the key idea really is that you understand what the baseline is for you and you want to see how you improve. If there's a systematic 10% error, for example, in it, it doesn't matter. If you consistently think you're producing 10% too much or too little, in the end what you want is you want to decrease the amount. And that you can see as long as the systematic error is constant. An example here, another example, that's another tool. This is not actually doing anything with measurement or it's purely estimation. It's a web-based tool and you can enter data here about the hardware you're using, and you will, if you remember, I showed you the stable diffusion numbers. I'm just putting the data in here. So I'm saying I want to have the A100 GPUs, I want 150,000 hours in AWS in US East. That is exactly what Stable Diffusion have said they did. And they, if you remember, they said 11 tons of CO2 emissions. The tool estimates 13.8. So you can see there's a deviation clearly in there. But at the same time, the tools are usually close enough in the same ballpark that if you keep consistently using one tool and you can show that you're improving, you can be relatively sure you have made an improvement. There is some ongoing work in trying to take a bit of the guessing out, a bit of the estimating, and make it more measurable. There's a really cool tool called Kepler. It works in Kubernetes clusters, and what they do is, it's open source software, what they do is they take the underlying implementation on the PC main boards that give you the actual power use. I don't know how many of you have a gaming PC, but on a PC you can ask it, how much watts of electricity are you currently using? How much is the graphics card using? And you get real data back. That tool, Kepler, is using that data, and then of course it knows exactly at a given moment in time how much electricity is the server really using, no estimation involved. What it then needs to do, it needs to do attribution. What is actually running on the server? It's a Kubernetes cluster. Any pod could be running on that node, and they use something really clever. They use the eBPF, the interface that was originally designed for firewalls, but is now used for a number of different use cases. They use eBPF to figure out what pods are running, how much CPU time they're using, and then can do relatively precise attribution. It can say the server is now using 400 watts of electricity, and it's the pod for the shopping cart that is running, and therefore, in a given different time window, for like a minute, and they can attribute exactly how much electricity that Kubernetes pod has used. So there's no real estimation in there. Only works, of course, if you have access to the real hardware. If you're running Kubernetes in the cloud or a managed Kubernetes server, Kepler will still work, but then it has to fall back, of course, to estimations as well. Maybe the cloud providers build something like that into their solutions. Let's see. So, finally, I guess you probably have, I hope, you have some ideas of how you could change the way you write and operate software already. But I want to give you a bit more of inspiration in the remaining 20 minutes. First off, though, there's two fields, or there's one field, I guess, that many of you are familiar with, a field called FinOps, financial operations. And that, of course, has to do with the reduction or the optimization of the cost of running software, usually in the context of cloud computing. So organizations, and there's multiple companies, specialized consulting companies, tools, etc., to just find out how much are you using, how much of the cloud resources are you using, and how can you reduce the cloud bill at the end of the month. And similar to that, there's now GreenOps, which goes in a similar direction, but it looks at the energy and emission optimization. The good news is there's a huge overlap. In fact, it's probably bigger than I'm showing on this slide here, a big overlap between the two. Because if you're using a lot of cloud resources, chances are you're also using a lot of electricity. So most of the time, these things go in the same direction. That's not always the case. For example, you might shift your workload, as I mentioned earlier, and maybe you're saying, I don't want to run this in US East because I know the CO2 footprint will be higher. I want to shift this to Finland, but the same servers might be more expensive in Finland. So there would be an example where you are becoming greener at the expense of spending money. But most of the time, it's really quite cool that by saving money, you're also doing something good for the environment. That's often counterintuitive. Most people think when we do something good, something bad will follow, right? If we want to be greener, we have to spend money. But in IT, for many, many cases, it's actually the proverbial win-win situation. Spending less money makes you greener. For all of that to work, of course, you do need metrics and reporting at the bottom, some solid metrics and reporting that I talked about. If you're in one cloud, by all means, use the tools provided by the cloud provider. If you're across multiple clouds or on-premises, use another tool that supports that. What is important, though, I wanted to show you this slide. What is important, though, is that you actually look at carbon efficiency as an architectural characteristic. I guess most of you are already aware, or if you are deploying software into public clouds, you will have engineering leads who are saying, please think about how many cloud resources the solution is using. I certainly remember one case of a client where I was personally involved, where we scratched an entire feature because of the cloud cost. The idea, we did some back of the envelope calculation and said to implement that feature, this will add so many thousands of euros to the cloud cost at the end of the month. And the business people said, if it costs that much to run, we're not interested in actually having that feature because it's not going to make that much money. So the idea of looking at run cost, I think, is pretty entrenched. A lot of companies are comfortable and used to looking at the run cost. And what we've said, this is from the Thoughtworks Technology Radar, actually a few years ago in the October 22 edition, we said, in the same vein, when you're designing systems at a large scale, do think about carbon efficiency when you design the architecture of the system, because you can often make significant changes at that early stage. So, I mean, one thing I can say is public clouds actually do help with reducing emissions. We talked about the data center efficiency earlier in the Etsy case, where an on-prem data center had a PUE of 1.4. The three big cloud providers that we see here in Europe, they are all around 1.1, 1.12 or so. So that's a significant improvement. And I think most data center operators will be challenged to achieve a PUE as low as that. But one thing that is also not to be underestimated is this elasticity of the resources. I mean, if you are an e-commerce company or a company that has uneven load requirements, you have to buy the hardware for the maximum case, obviously. When you're in a cloud, the computers can be used for something else when you are not using them. I mean, this is how the whole cloud computing started with Amazon, right? And I mean, that means that other people can use spot instances to run software when nobody else wants the servers. You can use something like function as a service to actually reduce the fabled scale to zero, that when you're not doing anything, you're not paying anything, you're not using any electricity. Remember the proportionality I showed you? An empty server that is idle still uses electricity. If you are using something like that in a large public cloud, your function isn't running, you are actually not really using electricity because somebody else is using the server, and the servers can be optimized. And then last but not least, in a public cloud, it's relatively, not trivial, but relatively easy to do this workload shifting, right? Hopefully everybody's doing infrastructure as code, and it would often just be a change in the variable to say, I want to deploy to that availability zone or to that region instead of another one. Whereas if you are operating your own data centers, then you have built your data center in one place. There's no shifting of the data center, right? So that is something that is also quite easy to do. Other things you can do, not related to the public cloud at all anymore. Resource scheduling. So sometimes we just don't think about this, and I mean, the simplest example is CI servers or continuous delivery servers. I mean, they're often kept running, or you rent the instances from the cloud providers, or you have the servers running yourself, and they are there 24/7. That's, and I need to look it up, I can't do the math in my head, 168 hours a week if you run it 24/7. If you are generous in saying the engineers are working in a window of, say, 10 hours a day, some start earlier, some work a little bit later, 5 days a week, that's only 50 hours. That's a 70% reduction right away if you're only making the hardware available when you actually need it. If you do a bit of attribution, because you could argue, of course, these CI servers are not doing anything overnight, so they're using less electricity. I did some math, and in the end, you still see a 40% reduction if you can return the servers. And you don't even have to do anything clever. You can write a very simple script to say, at, I don't know, 7 p.m., remove all the worker agents, except maybe 2 for emergency patches, and then at 7 o'clock in the morning, you're ramping up to 10, 20 build agents again. Very simple stuff. And I guess this example lends itself to be worked in other areas as well. Something that is a bit more involved, to give you an example of, you can also think in different directions. One thing we've often seen is in Hadoop clusters, you have two things that need to scale. In a Hadoop cluster, you need to scale compute and storage. But if you have them both in the same server, you might have to add new servers when you're running out of disk space, but the CPU isn't fully utilized. Or your CPU is fully utilized, but your disks are still empty, and you still need to scale. You need to scale with a larger number at the expense of the smaller one. So for example, you could split storage and compute, and Hadoop allows you to do that. So you could say, if we're running out of compute power, add more compute nodes. If we run out of storage space, add a few more storage nodes. So again, just thinking about what are the factors involved, and can they scale independently, and what does it mean for our hardware is usually a pretty good idea. Then, here's a nice case study, reorganization of batch jobs. I don't know how many of you work in financial services. They still love batch jobs. Other industries have them too. And there's a case study that was done by Microsoft and UBS together with the Green Software Foundation, and they looked at that in more detail. And what they did is, here's the corresponding chart, they looked at a number of days, and here in red you can see the amount of CO2 that would have been produced when they ran the batch job at the predetermined time. Let's say they always run it at 2 a.m. in the morning. And then on September 19th, in the red line, you can see how much CO2 they would have used. What they then did is they used weather forecasts, and there are also available forecasts of the carbon efficiency of the grid, and said, what is the optimal time to actually schedule the batch job? Maybe not 2 a.m., because the weather forecast says there's going to be more wind, therefore the grid will have greener energy. Maybe we run this at 3 a.m. or 3:30 a.m. So this was then the optimal prediction, this gray bar here. Of course, a prediction is a prediction. Weather, as we all know, changes. So then in the yellow line, this is what they actually, based on the data that was available, caused at CO2 emissions. So you can see here, that's without any optimization. That's what they thought they would optimize for. And in that case, they even came out better. That's not always the case. Here, for example, on the next day, this was the original prediction. Taking into account the prediction of the CO2 efficiency of the grid, they thought they could get here by rescheduling to a different point in time. In the end, it was slightly different. It was higher than estimated, but still better than running at the original time. So again, this is just an example to show you what you can do without too much effort. I mean, of course, they needed to figure out how long do the batch jobs run. I mean, if the batch job takes 4 hours, you probably can't run it at 6 a.m. because you don't want to run it into the business day. But I mean, with relatively simple, small projects, you could actually save, in this case, the CO2 emissions, not so much electricity, but in other cases, you can do that too. I mean, there's a whole talk maybe in there in optimizing batch jobs. I don't know whether you've seen it. Batch jobs that are run indiscriminately. The input data isn't changing, but somebody's just running the batch job just in case, or maybe forgetting a cache about it, and so on. So there's a lot of other things you can do as well. But not to bore you too much with that, I want to go to something that has to do with AI. And that's machine learning training. So I mentioned early on, there's a lot of machine learning now. And here I'm using a slide that is, I think, a few months old from Google, because it is actually good and sound advice. So I just want to give you an example of what you can all do in machine learning when you're building all these models, when you're using all these machine learning algorithms. I'm not going to go through all those bullet points, that would take way too long, but I just want to highlight a few of them. The first one, leverage existing models. I mean, there's TF Hub, for example, but as I said, there's Hugging Faces. There are so many different places where you can find foundational models. And it's not only easier and more energy efficient, but it also saves you a lot of headache and deep insight you need to do to actually train models well. We've really moved away with most of the clients we're working with from training models and using foundational models. I mean, simple things, of course. Don't run this on a normal CPU. Use GPUs, TPUs, NPUs, whatever they're called these days, to actually make the computations more efficient. I don't know how familiar you are with the field of machine learning. There's these mythical hyperparameters. These are parameters you're setting up front on the machine learning model before you actually do the training. But of course, that's also a search space, and sometimes you don't know what hyperparameters you use, so that's the space you have to explore, and that is one of the areas that is really tricky to do, and you can, I mean, maybe you need to try, I mean, you do say Monte Carlo simulation, you're trying random combinations of different hyperparameters, and you're doing hundreds of those to train the model and see, is the model getting any better? But you heard it, hundreds. You're training not the model once, but you have to train it 100 times, as an example, to find a good match. So again, there are good solutions. There's a tool made available by Google called Bezier or Visor that actually helps you with that. Yeah, and then here at the bottom, the thing I said multiple times now, train with regional and time-specific carbon emission impact in mind. Do think about where and when you run these, if you can afford it. And I would argue when you're doing machine learning models, you can almost always afford to run it at a good time. And even pause it maybe. Use spot instances if you can, because these machines are there anyway. They're just waiting to be used to get out of that 10% into the 80% super efficient load factor for the machines. Not to leave it completely to Google, AWS also, I don't know whether you know it, they have the well-architected framework. That's actually a helpful resource regardless. I would say the addition that they made came out, I think, last year about sustainability is actually quite helpful. There's nothing earth-shattering in there, but I do think it is, and you can see it from some of the headlines I'm showing here, it's a really, really good checklist to run through and think, and even if you're on a different cloud or on-premise, it's a good checklist to think, are we actually doing the right thing? Have we considered that? And there might be good reasons why one of the things here, for example, implement buffering or throttling to flatten the demand curve. You're like, no, we can't do that given on the business case we have, but it can be really used as a checklist to think, have we considered that? Because in other cases, you might think, oh yeah, we could actually do that. Why didn't we? And it becomes obvious in hindsight. It helps you to ask the right question. And I made this so you can read them. The overall list is actually that long. It's not too long, so it's actually manageable, and in our experience, absolutely useful to go through. Yeah, and that's all I had for you. Thank you very much. I don't know, this is a keynote. Are we doing questions or?
Yes, we have a few questions on Slido.
Okay.
Will you open Slido?
Can I open it? Oh. Yes, I can. No? I'm probably logged into our slide. Oh, it works. And it's just GeeCON.
Here is the room number 1. You can read from
Okay.
from my
Okay, thank you. Okay, I'm going to go by the upvotes on the question, and the first one is a little bit predictable. It is, how much of that 1.5% of global energy consumption is due to Bitcoin mining? I don't know. I don't know the answer, and I think it depends vastly. Sometimes, in the best cases, some of the Bitcoin mining actually went into places that were otherwise completely unused. I mean, I don't know whether you've seen those pictures of these makeshift server rooms somewhere in a remote mountain area where there was a water river and they just stuck a turbine in. That was, of course, free. But there's also the stories about North America where they were going to, I don't know whether they actually did, restart defunct coal power stations just to mine Bitcoin. So I don't know. I don't know how much it is. It's probably noticeable, but not the largest factor here. And also there's a massive change in how that landscape worked with the finally the switch that Ethereum did. But on the other hand, I don't know what all that Bitcoin is being used for and what the blockchains are being used for. And now the phone locked itself. Maybe.
Sorry.
No worries.
So the next question
I will move my finger. So the other question is, why not use on-prem data center powered by solar power plants instead of moving to super expensive public cloud omnipoles? Do the math. Maybe it works for you. As I said, I mean, there's a couple of things to be considered. On the one hand, there's also the use of the hardware. If you're running on-prem and you have spiky load, if your load is not even, if you have load spikes, you have to have enough servers available for all the spikes, which means there's a lot of surface area in your chart where the servers are sitting there not doing anything, which of course counts against you because all those servers have to be produced. If on the other hand you're running something that has very, very constant, very predictable workload, maybe you can do that. Maybe you can even say, for one reason or another, we can use the servers for 6 years instead of whatever the cloud providers are doing, and you're saving some money. It is a possibility. Running data centers is getting harder. A lot of development teams, a lot of modern architecture presumes a lot of things that the public cloud gives. And I don't know about you, I've not seen many successful implementation or any really super successful implementation of private clouds. So again, if all you need is a couple of virtual machines, like Linux virtual machines that run, say, Java software, maybe that is an option for you. In many other cases, it might not be the best option. And again, as I said, I mean, FinOps and GreenOps have an overlap. Sometimes it can be more expensive. In many cases, it's cheaper. So you got the consultant answer, right? It depends. Yeah, there's another question in the same direction. What about the trend nowadays to move out of cloud because of the very high cost compared to run your own hardware? I see this a lot. I'm an engineer myself. It depends on what you really want to do. I mean, you can say, we can run the same thing 10% cheaper or 20% cheaper, but then you have to hire people. That is also cost. You have to have people who run the cloud. Sometimes it takes a longer time. I've seen a lot of delays in large enterprises who went down that route and said, we do want to run this on-prem data centers. And then you have things like something works on one node of the Kubernetes cluster, but it doesn't work on another node because the infrastructure as code scripts aren't as good. They don't have as much experience in building that. They don't have the same optimizations between how the servers are in the racks and the switches, the network switches and so on. I've seen people say, I can run this for 10% of the cost as a public cloud. And then if you look at the numbers, they just really don't stack up. So I agree with you that a lot of people are surprised. I guess they were sold on go to the public cloud and everything's going to be cheaper. That's not what we're seeing. But now I think the pendulum is swinging a little bit in the other direction, where people are saying, oh, the cloud is super expensive, we can do it cheaper, but only taking a fraction of the actual cost, leaving the salary cost, leaving opportunity cost, response time, etc. out. Not an answer that is really related to green computing, because as I said, most of the things I talked about, you can actually do in different scenarios, be that public cloud or an on-prem data center. That's an interesting question. If we are serious about carbon footprint, should we all move to GraalVM native image? Again, I think if you can find a solution where the trade-offs work for you, where you're using less electricity, where you can make the software more efficient at runtime, absolutely do that. Is that the number one factor? Probably not. But as far as I understand, I've not used GraalVM myself. It is much of a drop in replacement, so that would sound like a good idea in many cases. The Q&A is gone now in room 1. Time's up. Thank you very much.